So section 2.3 is all about applications of first order differential equations and how we can solve new kinds of problems using these concepts of first order linear and separable equations. So the first thing I want to look at here is projectile motion. In Calc 1, we do things where we know a position function as a function of time, and then we figure out that, hey, if I take the derivative, that's going to be telling me the rate of change in position with respect to time, which is velocity, and the derivative of that would be the rate of change of velocity, of course, which is acceleration. In Calc 2 class, we can work that backwards. We can say, okay, what if I know about acceleration? I can do antiderivatives to find velocity, and then another antiderivative to do position. So it would look something like this, your standard. When I sped this up, it changed the audio, so this is dubbed afterwards. I'm just explaining how if you have, it's all review, so if you've got constant gravity, then you integrate to find the velocity, and you plug in an initial condition to get the initial v0 at time 0, and then you integrate again to get the position, and of course if you had some initial height, then at time 0 you'd be at height y0, and that's all that's happening here. So a graph of something like that is a parabola. It's an upside down parabola, like here, this is a minus sign in front of the t squared. Initial height at time 0, and toss it up into the air, it comes back down again. This was always done under the assumption that there's no air resistance, right? And you can see things like, from the time it starts off to the highest point, just the way I have this one drawn, it changes from 5 to 10 in height, and it does that from time 0 to time 5. In the same amount of time after the highest point, from 5 more, it comes back down to exactly the same level it was. That is, the time it takes for an object to go up so far is exactly the same amount of time as it takes to come back down again afterwards. This has always been done with the assumption of no air resistance. And I want to know, when was the last time you tossed something into the air with no air resistance? Air resistance is there. We got to take it into account. Now we can. Okay, so here we go. And I'm going to ask the question, if there is air resistance, this thing as it moves upwards and then comes back downwards, which takes more time? So from the bottom of the screen to the top of the screen, or from the top of the screen to the bottom, going up or going down, traveling the same distance, which takes more time? Or are they the same? It's still the same like it was before. So let's see. So here we go. What are we going to do? So I'm going to assume that the force of air resistance is proportional to the velocity. You may ask, is this reasonable? It turns out it is, although there's other models that people use as well. But for this introductory model, I think that velocity is proportional to velocity is a reasonable thing. So the force of air resistance is equal to minus kV. The minus because it's in the opposite direction. If the object is moving this way, air resistance is pushing against it in the other direction, right? So whatever the velocity direction is, the force is in the opposite direction. The K involves a lot of different things. It involves how thick the air is that you're going through, or maybe you're going through molasses or something like that. It also has to do with the surface area of the object that's moving. So for instance, this little flower, if it's moving face on, it's going to have more air resistance than if it's going side on, because there's not much surface in the front. So this would have very little air resistance going that way, but it would have more air resistance going this way. So this K is taking a lot of things into account depending on the situation. What's the object that you're throwing? What's the medium that it's going through? Okay. So anyway, force, according to Newton, is mass times acceleration. So to find the acceleration, I'm going to take the force and divide by the mass. So take this divided by the mass. And what I get is K divided by M. The mass of the object moving is not changing. So that constant divided by mass is just some other constant. And so I'm going to just write it as minus little k times v. So the acceleration is just a constant times the velocity. This is the acceleration due to air resistance. Okay. So now the total acceleration on this object, if I throw it up into the air and it comes back down again, the total acceleration is the sum of the acceleration due to gravity, which is downward, constant g downward, and then the acceleration due to air resistance is minus kv. Notice that when k is positive, so it's going upward, the minus k is pointing downward, so it's pointing in the same direction of gravity. But when this object is coming downward and velocity is negative, the minus k times v turns out to be a positive term, and so that this part of it actually is pointing upwards. So with positive velocity, this is pointing downward, but with negative velocity, the acceleration is pointing upwards. That part of the acceleration, anyway. This is always pointing downward. Now, if that's the acceleration, then the acceleration is the derivative of the velocity. And what I have here is a first-order differential equation in v, right? I have a v here, and I have a dv dt there. So this is a first-order differential equation in v. It is both first-order linear, and it's separable. I could solve it either way. I'm going to choose to solve it as a separable equation here. So what I'm going to do is I'm going to divide both sides by this whole right-hand side. So there it is down in the denominator on the left now. And then I multiply both sides by dt. So dt, 1 times dt is all that's over here on the right, and everything else is over there on the left. So the format then, of course, separable equations. You got all the one variable on one side times dv, and all the other variable on the other side times dt. And now I'm going to integrate both sides. So integrate both sides. This side's a really easy one. Integral dt is just t plus a constant. This one, there's a u substitution with u equals this denominator. Du equals minus k dv. I have the dv, but I don't have the minus k, so I'm going to end up multiplying by 1 over k in the end here. And then I've got a 1 over u du, which would integrate to the natural log of u, and so I get this. Solving for v now, I multiply both sides by negative k. The c times negative k is just some other constant, so I'll leave it as a c. I'm going to exponentiate both sides to look like this. Then the e to the sum of those two exponents is the product of the individual e's to those exponents. But then e to the c is a positive constant, where just c is a positive or negative constant, which allows me to get rid of the absolute value signs. I can then add the g to both sides. Sorry, I had a little bit of a, it's like, did I do this wrong? Because when I move the g over the other side, it should become positive, but then when I divide by the negative k, that becomes negative again. The c here, of course, would be c divided by negative k, but that's still a constant. So since I haven't solved for it yet, I'm just leaving that as a c. Now, if I had some initial condition, so at time 0 I have some initial velocity, I can plug in those initial conditions and figure out what c is. So e to the 0 times c plus negative g over k is the velocity at time 0. And solve for c, we get this, and I end up with a velocity equation that looks like this. Minus g over k plus this thing. Now, notice this is a decaying exponential. So what's happening as time goes on, as t gets bigger, this exponential is approaching a horizontal asymptote of 0, right? And so this term gets smaller and smaller and smaller, approaching 0 as time goes on, and the velocity is approaching minus g over k. Now, maybe if you know anything about falling objects with air resistance, like parachutes and things like that, there's this thing called terminal velocity. It's this velocity that I always thought in terms of parachuting, it's like, yeah, it's the velocity at which you die, right? No, terminal velocity is essentially the horizontal asymptote of the velocity function. As time goes on, the velocity approaches minus g over k. Okay. So now that you have a velocity function, you can find the antiderivative to get a height function, a position function, right? So doing the integral of the velocity, we get this. So this part here just is the minus g over k times t, and then this exponential would do a u substitution with u equal that exponent, so you end up with an extra minus 1 over k in the denominator, so the v0 over k and the g over k squared, and the minus sign I left out in front there. Right? And then, of course, there's a plus c, which you would figure out the plus c knowing some initial condition. How high is the thing at time 0, for instance? You could plug in a 0 for t, an initial height of s0 or y0, whatever you want to call it, and figure out what c is. I want to take a look at the graphs of these things and see how it differs from the quadratic that we got up above, right? Both how it differs and how it's the same. So first of all, the velocity function. I just made some quick assumptions here. Suppose v0 is 4 and g over k turned out to be 2. And I picked k being like 0.1 or something like that. So it's a really slowly decaying exponential, just to stretch it out and let you see what's happening. I've got a few graphs drawn here. The black one is just the e to the negative kt, just this decaying exponential. All the exponentials like that pass through the point 0, 1. They have a horizontal asymptote of 0, and heading uphill on this side. Now, when you multiply by, so I'm looking at the velocity here, so when I multiply by this number here, it's going to just scale the graph by a factor of that in the y direction. So where the y-intercept was 1, it's now going to be v0 plus g over k. So in this case, it's going to be 6. That gets me up to this blue one. So the blue one is just the scaled up version of the black one. Notice that scaling up a horizontal asymptote of 0 still gives you a horizontal asymptote of 0, because 0 times anything is still 0. So this thing is scaled up here, but then down. Now the effect of the minus g over k is to take that whole graph and shift it down by g over k. Well, in this example, I had g over k was 2, so it shifts down here. And notice then that at time 0, we're at 4, which is what I said the velocity should be 4 at time 0. So we get this gets back down to the appropriate starting point, but also it shifts now. It shifts the horizontal asymptote down by whatever g over k is. So now there's a horizontal asymptote of negative 2, and so the terminal velocity in this example would be negative 2. Now the height function. When I look at the height function, which is this thing, there's a linear piece, a downward sloping linear piece, and an exponential piece. It's a decaying exponential, but it's upside down. That is this negative sign here. So there's an upside down decaying exponential, and there's a downward sloping linear function. They're added together, and the net result looks like this. Okay. Now notice, to start with, this is coming uphill, and if there was no linear piece, this would come uphill and it would just have a horizontal asymptote up here somewhere. And that horizontal asymptote essentially is that whatever the plus c turns out to be. If I didn't have this linear piece, whatever that plus c is, that would be shifting the graph upward. That upside down exponential will be shifted up to an asymptote of whatever plus c is. But there is this linear piece. And so as time goes on, as this exponential decays and becomes closer and closer to 0, you're just looking at this linear function minus g over k times t plus whatever that constant is. And so eventually it starts looking like a downward sloping, this thing just keeps going down and down and down and down, right? It's a downward sloping linear function after at least it approaches that. So it starts off as an upside down decaying exponential and then transitions into a downward linear function. The last thing I want to notice here is that notice from time 0 to time 4, we climb from a height of 3 up to about 5, and then to get back down to 3, it takes us clear out to here. So that was 4 units of time to get to the top, but 1, 2, 3, 4, almost 5 to come down. So it took longer to come down. This makes sense to me because when you're going up, both gravity and air resistance are trying to slow you down. They're working together. But when you're going back down, gravity is still pulling down, but air resistance is pointing up, and they cancel each other out. In fact, eventually, there's so much air resistance that it precisely cancels out gravity, and you aren't accelerating. You keep moving at the same speed. That's called terminal velocity.